In this video, we're going to look at a brief overview of resonance structures. Now, resonance structures, how do I want to say this? In this video, we are going to look at resonance structures, and we are just going to cover these very briefly and not super in depth. Now, resonance structures show how electrons move in molecules with double or triple bonds. Something that is very important though is that not all molecules um, have the ability to have resonance structures just because they have double or triple bonds. So let's look at an example. In order to draw the resonance structures, you first need to look at the Lewis structure. So let's draw the Lewis structure for carbonate. Carbon has four valence electrons, and we have one of them. So that'll give us a total of four valence electrons from carbon. Oxygen has six valence electrons, and we have three of them, which will give us a total of 18 valence electrons. Now, this is different than the ones that we have done so far because there is a 2 minus charge. Now, to compensate for that 2 minus charge, we are going to add electrons. So since it has a 2 minus charge, we are going to add 2 electrons. So when I add that up, I'm going to get a total of 24 valence electrons. This compound only has two atoms, so the first atom is my central atom. I'm going to put carbon in the middle and then draw three oxygens around the carbon. Then I'm going to attach the carbon to each one of the oxygens. When I did that, I got a total of six bonding electrons. So it can subtract six bonding electrons. And I will have 18 valence electrons left over. I'm going to start on my outer atoms first. I'm going to fill their valence electrons. And when I do that, I can fit 18 around my oxygen, so I don't have to worry about putting any more around the carbon. My last step is I'm going to check my octets. All of my oxygens have six lone pairs and one bond for a total of eight electrons. However, carbon only has three. So I need to take a lone pair and form a double bond. This is where you might be asking, which one do I choose? It really doesn't matter because this is where we're going to see our resonance structures. Double bonds are usually closer together. The atoms are generally closer together because there is more electron density. So a double bond is going to be shorter in length than a single bond. However, when you look at the bond length of the CO bond in carbonate, all three bonds have the same length. And that's because you have this constant movement of electrons from one double bond to another double bond. So this is my Lewis structure of carbonate. Since there is a charge on it, I'm going to put brackets around it and I'm going to put a 2 minus charge outside of the brackets. But what we need to realize is this double bond is going to move throughout my entire molecule. So I can take the electrons from the double bond and put them back out on the oxygen. And then I can form a different double bond from one of the other oxygens. And hopefully you can see when that happens, I've moved the double bond from my oxygen on the left, and now it is going straight up. My double bond has moved from here and is going straight up to here. I can move it one more time. I can move it here. So I can take the lone pairs of electrons from that oxygen and I can move the double bond electrons. And I can get my final resonance structure. Since there is a -2 charge, I'm going to put brackets around all of my resonance structures and put out the charge here. So the big thing that you need to pay attention with resonance structures is I didn't do any chemistry. In every single one of these compounds, I have carbonate. I have carbonate here, carbonate here, and carbonate here. I didn't change the identity. Resonance does not change the identity of the molecule. It does not change the identity. So I can't do something like break a single bond because that's going to change the identity. I can only move this double bond throughout the molecule. Now, resonance has a very stabilizing effect, and it can be a little dangerous when you're looking at the different molecules that can go within our body. So, for example, benzene, man, my pen really wants to draw all these extra things right now. Benzene is a six-membered ring containing only carbon, and it has alternating double bonds, which means that we can have resonance structures. I can move those bonds to a different location. Well, this is a very stabilizing effect, and benzene is going to be very stable. The other thing about benzene is that it is very, very flat. So benzene can be really dangerous to us as human beings because it can disrupt the attractive forces that hold our DNA in a double helix. It can get in between those attractive forces and cause our DNA to not be in that helix anymore. All right, let's look at another example. We have CH2O. Yay, this is a fun one. We haven't had one that has three atoms in it yet. So I have carbon for a total of four valence electrons. I'll get two from hydrogen because it has one valence electron, and there are two of them, and then six from oxygen, which will give me a total of 12 valence electrons. When you have three atoms in your molecule, generally the atom written in the middle is going to be your central atom. But if we look at our atom in the middle, it's hydrogen. So it can't be hydrogen, so I'm going to go with the first one. So I will draw my carbon in the middle. I'm going to use a different color so I don't get it mixed up with carbonate. And then I know molecules like to be symmetrical, so I'll draw a hydrogen on each side, and I'll draw this oxygen going up. My next move is to attach my carbon with all of my outer atoms. I drew three lines, so it is going to be a total of 6 electrons. I will subtract 6 bonding electrons from my valence electrons, And that means I have 6 valence electrons left. I'm going to distribute that on my outer atoms first. And I've used up all of my electrons and made lone pairs. So I've used all my electrons. Now I can check my octets. Both hydrogens are happy. They only want 2 electrons. They have 2 electrons. Oxygen is happy. I have 6 electrons from my lone pairs, 2 electrons from my bonding for my bond, so a total of 8 electrons. However, carbon is not happy. So I'm going to form a double bond between carbon and oxygen. So now I can ask myself, is there the ability for resonance? Can I move this double bond? For the answer, for this molecule, the answer is no, I can't. I can't have a double bond between hydrogen and carbon because that would be too many electrons around hydrogen. I can't move it to any of these places. So the double bond has to stay there, meaning there are no resonance structures. And there's no resonance structures because the double bond can't move anywhere. In carbonate, I can have 8 things around oxygen. So I can move my double bond to this oxygen here, and then I can move it to the next oxygen. I can move my double bond, there are resonance. There is nowhere for me to move the double bond because there just isn't room.